Hello everyone, I'm Zhengpeng Cheng from Peking University. In this presentation, I'm going to talk about our recent work on deployment force of deep learning-based mobile applications. In recent years, deep learning has been widely used in mobile applications. These deep learning-based mobile applications, namely mobile deep learning apps, are not only used by billions of end users for their daily activities, but also reported to be increasingly adopted in safety-critical scenarios. To achieve powerful mobile deep learning apps, developers need to deploy well-trained deep learning models to mobile apps. The deployment process can be divided into the following stages. First, developers use specific deep learning frameworks such as TF-Lite and CoML to convert trained deep learning models to the formats supported by mobile devices. After the deep learning model is converted into the expected format, developers can integrate it as well as deep learning frameworks into a mobile app project. Then they can build the project and load the model to make it ready for inference. Finally, the deployed deep learning model can make inference based on the input data. Once put into real usage, mobile deep learning apps keep receiving feedback from users and further improve the models. During this deployment process, various specific forces are emerging and frequently encountered by developers. We call these forces deployment force of mobile deep learning apps. However, the characteristics of these forces have not been well understood. To bridge the knowledge gap, this paper analyzes how deployment forces of mobile deep learning apps are resolved by developers in practice. Specifically, we focus our analysis on two research questions. In the first research question, we studied the frequent symptoms of deployment force of mobile deep learning apps and construct the taxonomy accordingly. In the second research question, we distill common fixed strategies for different force symptoms. To answer the two questions, we collect real-world fixed cases of deployment force of mobile deep learning apps from Stack Overflow and GitHub. Specifically, we extract Stack Overflow questions and GitHub issues related to TF-Lite and CoML. Since TF-Lite and CoML are both representative frameworks specifically designed for deploying deep learning models to mobile apps. Then, we refine the collected dataset by removing questions and issues with low quality and ambiguity. Finally, we have a dataset of 304 real-world forces for analysis. Based on the dataset, we follow an open coding procedure to manually label each fault with a symptom and a fixed strategy, and then answer the two research questions. Let's first look at the results of the first research question. Here is the hierarchical taxonomy of deployment fault symptoms of mobile deep learning apps, consisting of 23 symptom categories linked to the 5 stages in deploying deep learning models to mobile apps. Most of the fault symptoms occur in model conversion and inference stages. Next, I focus on the faults that occur during the 2 stages. About half of the deployment faults occur during the model conversion stage, covering 11 frequent symptoms. Among these symptoms, unsupported operation is the most common. After parsing the deep learning model, the converter may find that the model uses operations that are not supported by TF-Lite or CoML. The common occurrence of unsupported operation errors is because that, compared to the frameworks used for developing deep learning models, such as TensorFlow and Keras, TF-Lite and CoML are proposed later and relatively unfledged. Therefore, some standard operators and functions used in the model may be not supported by TF-Lite and CoML. Moreover, a large proportion of faults occur when the converter parses the deep learning model and validates the model information specified by developers, such as names and shapes of input and output tensors of the model. In addition to the symptoms specific to the deployment of deep learning models, we also observe that a portion of faults share common symptoms with general software systems, such as the attribute not found. There is around 36% of deployment faults do not show symptoms until making inference. Some faults appear with explicit errors, such as a shape size error. They are triggered when the shape or size of the arrays used for storing input-output data does not align with that of the input-output tensors of the deep learning model. Furthermore, deep learning app often produces unexpected results, although no errors are thrown. For example, developers may observe that the mobile deep learning app produces different results than the original model. In addition, there are also some faults that have impact on the memory usage and inference speed of mobile deep learning apps. Next, let's move to the results of fixed strategies. In this part, I will also focus my introduction on faults in model conversion and inference stages. We use the heat map figure to show the frequency of each fixed strategy on each symptom category. In the figure, x-axis represents different symptom category, and the y-axis shows fixed strategies following with their total frequency. In each cell, if it is darker, then its frequency is higher. For faults in model conversion, we identify 9 frequent fixed strategies, among which fixing framework installment or version is the most common and especially frequently adopted in the unsupported operation category. For example, many unsupported operation faults are fixed after switching the deep learning framework into a more recent version with more supported operations. Another strategy I want to mention is repairing the deep learning model used for conversion, which mainly tackles the unsupported operation and shape size error. For unsupported operation, developers can replace it with a supported one, implement its function outside the model, or delete it if it is unnecessary. As for shape size error, we select a real-world core ML issue as an example. In this example, a developer uses Keras to train a binary classifier. However, when she converts the obtained model to the core ML format, shape size error occurs. Since he specifies 2 output labels including 0 and 1 during model conversion, the converter expects a model with a 2-dimensional output tensor. However, the output of the original model is a 1-dimensional tensor, indicating the probability that the input is classified as label 1. To resolve this fault, the developer repairs the original model and makes it output a 2-dimensional tensor. For the faults that occur during the inference stage, we identify 13 fixed strategies, covering many stages of the deployment process, including fixing data processing, fixing model conversion stage, and fixing deep learning integration stage. In addition, we note that repairing the original model is a common fixed strategy not only for faults in model conversion stage, but also for faults occurring during inference. It mainly resolves the shape size error and unexpected result. Specifically, when the input size expected by deep learning model is inconsistent with the actual size of data extracted in apps, one solution is to reshape the original model. Moreover, some developers find that the models cannot perform well in real applications, and thus choose to refine their original models. At last, I'd like to give a quick summary. In this study, we analyzed real-world faults related to deploying deep learning models to mobile apps collected from Stack Overflow and GitHub. We construct a taxonomy of 23 symptom categories and distill common fixed strategies for different fault symptoms. Our results can serve as a guide for developers to resolve common faults, and for researchers to develop tools for detecting and fixing deployment faults of the increasing mobile deep learning apps. You can find more details in our paper if you are interested. Thanks for your attention.
Welcome everyone to the backstage question-answer session. My name is Mika, I'm the session chair, and we have Chen Peng here to answer all of your questions. Okay, checking the chat. I don't see any questions so far, but maybe I can get started while we wait for the audience. So this was about deployment faults of deep learning-based mobile applications. When I see the word deployment, it sort of really connects me with continuous integration, continuous build, continuous deployment, continuous delivery. Was it typical for these faults that they rise from the, let's say, the continuous integration cycle? Was there anything like that in the data?
In this paper, we use deployment force refer to the force that recur during the process that deploy deep learning models on mobile devices.
Okay, but was it sort of part of the? Yeah, please go ahead.
To achieve a workable deep learning, we can divide the process. We can divide the process into two stages. The first stage is train deep learning models, and the second is to deploy deep learning models on the real platforms for usage. So the deployment of deep learning models is referred to the stage.
Okay, but did you analyze anything about, was it part of this sort of continuous integration delivery pipeline, or is it sort of like separated from that sort of software engineering integration deployment, that type of stuff?
Similar to the traditional definition of deployment in software engineering. The traditional definition, deployment refers to the process that deploy the software that have been well tested on the target platforms for real usage for the users to use. And why we use deployment to refer to the process that after deep learning models are demonstrated and tested to meet the performance requirements, we are ready to deploy them on the mobile devices for real usage. So I think the process is similar to the traditional definition of deploying software.
Okay, thank you. Okay, we have a question or comment in the chat from Wenxing Yang. He says, "Hi, thanks for your very nice work. How did you define high versus low quality questions issues from Stack Overflow / GitHub? Does others contain those faults with only one account? It seems like a little large percentage of others in your work." So maybe you can answer the first question first and then the second question.
Yeah. First question is, how did you define high low quality questions from Stack Overflow GitHub? Yes. Actually, there have been a standard way in software engineering research community to identify the related questions on Stack Overflow and GitHub related to interested topic. In this work, we follow the previous works to identify these questions. For example, since deep learning software deployment on mobile devices are mainly relied on specific deep learning frameworks such as TF-Lite and CoreML. So we first identify the questions and the related questions and issues that are tagged with the two frameworks, and then we felt that we use the questions and issues that have confirmed the solution, and view these questions of high quality questions and issues. The others in the taxonomy means that refer to the low frequency questions and the issues, and in this paper, they are less than 3 times, occur less than 3 times.
Okay. Was there anything about there was a taxonomy on the what type of errors they have, like invalid argument, unsupported operation, and so on. But was there anything about where they detect these errors? Like, is it in the unit testing, or is it in the field testing, or at which sort of development process did they find these errors? Should I repeat the
Can
question?
you repeat the question?
Yeah. So I was wondering at which point were the errors detected? So did they detect them, in unit testing, or were they already deployed in the devices and they find them, or were they like compile errors where the whole thing just doesn't even compile, or do you have anything about that?
Covers the many stages in deploying deep learning softwares to deep learning models to mobile devices, such as model conversion, deep learning integration, and inference.
Oh, right. So okay, so it's over there. Oh, okay.
Next question: to what extent these was caused by the fact that these are AI approaches, as opposed to the implement that could happen to no, this was caused by. Okay. Actually, in our constructed taxonomy, we cover both the force that related that specifically recur in AI based systems, and we also cover some force that can occur in general software systems, such as attribute not found error. However, most of the force that contained in our taxonomy are about AI systems. Oh, okay. To extend are caused by that.
Yeah, so you would say that they are AI specific.
For example, the force that occur during model conversion are mainly about AI systems, such as model parse failure, tensor error, shape size error, and also a small portion of force can be found in general software systems, such as attribute not found, invalid argument, and import error.
Okay, there is a question that we sort of missed. So Meijin Liu asks, hi, thanks for your nice work. I noticed that there is one fault named model update in your paper. Does this mean retraining model will lead to mobile software bugs?
There's one fault named model. Oh, okay. Retraining will lead to. Yes. Actually, retraining deep learning models on mobile software is a very, very challenging task. Since that training a deep learning model usually requires intensive computation power and memory cost. However, the deep learning the mobile devices are usually lack of computing power and memory. So it is very challenging to retrain the deep learning models directly on the mobile devices. So
You have,
yes.